that's completely normal. I know certainly when I started doing step questions, I could kind of do, 10% of most of the questions, and then I had to give up. But very good job if you managed to get through most of it. This question is initially quite scary, I think, because it has this new thing written like, oh, hello, can I write, please? This thing written like this. It's called floor x, usually, and I'm assuming most of you wouldn't have seen it before. And that's new, so it's sometimes scary when you're presented with a new thing in a question. Certainly in A-level, you're not usually presented with something new. But actually, these kind of step questions can be quite nice, because if it's something new, they'll take you through some basic ideas with the new thing. Whereas if you are being asked questions on, trig identities, they can assume you know quite a lot about trig identities, and therefore the questions can be a bit more advanced, which is not to say don't do questions on trig identities, but you shouldn't disregard questions that have new things. It's also a hell of a lot longer than you're probably used to seeing for an A-level question. But I mean, it's split into lots of kind of bite-sized chunks. So often you find that although the whole question to begin with looks intimidating, if you go through and just take out bite-sized chunk after bite-sized chunk, the whole question can end up being solved quite nicely. So I guess we should start with the question. So yeah, when you're presented with a new thing, it's quite important that you try and understand this new thing. So in this case of this question, it's this floor x symbol. Now it has a lot of words here to describe this thing, and then it gives you some examples. So when you're given an unknown function, often quite a good way to try and understand it is to try and sketch it. So if we look at if we draw some axes rather terribly and label on some points, we can try and understand what this function looks like. So let's take a point, say here, and see what we think the function should evaluate to. So we're looking for the greatest integer that is less than or equal to x. Well, that's the greatest one of these points to the left-hand side of this cross. So that's going to be 0. So here, the function's going to be 0. And similarly here, and here, and here, and here. In every one of these points, the greatest integer to the left in it is 0. So in fact, we can fill in the whole of this middle section to be 0. Similarly, if we're in this kind of area, we can see that the greatest integer on the left of these points is 1. So it jumps up to 1. And similarly in the other parts. I'm going through this fairly quickly, I think, just because we used up quite a bit of time in the beginning getting on into rooms, and I do want to get on to the later stuff. So no worries if you think this is a bit fast. And then the only other question that's worth asking is what's happening exactly at these integer points. And that's when this or equal to part is very important, so that we see the greatest integer less than or equal to 1 is 1. So it takes the value 1 at 1, not 0. And when you have this kind of graph where it's ambiguous which value you're taking, one way that you can denote it is you put an open circle on the value it's not taking and a closed dot on the value that it is taking. I mean, you wouldn't need to do that, but it's one way to represent it. So that our function looks like this. And we see that actually all of those words just kind of mean draw a staircase. And I've got a computer to draw it for me. And there you go. There's a section of the floor function between -2 and 2 or something. And our sketch was pretty good. So moving on to the first part of the question. Is that good for everyone? Everyone see what I'm doing and kind of get what's happening? Yep, cool. At least one yes works for me. So the function f is defined for x not equal to 0 by fx equals floor x over x. Sketch the graph of y equals fx between -3 and 3. Well, to begin with, a good thing to do it would be to draw some axes between. Oh my god, that is okay. Let's draw better axes than those. Let's delete those, and then cheat by the fact I can draw lines. Draw some axes. Okay. Oh, zoom, go away. Cool. So, any ideas of initial approaches when you see something like this? Or what did you guys try if you had a go at it? Value table, yeah, that's sometimes good. Picking nice points to work with, yep, for sure. Asymptote x equals 0, all good ideas. Value tables are nice because they sort of give you an idea of what's happening locally, so sort of very nearby, but you can't, it's not true that you can sort of draw a bunch of points and then draw a smooth line through them and that be your graph, especially considering we've got this floor x kind of staircase thing going on. Oh yeah, does asymptote know what an asymptote is? When you sort of get close to an axis, or well, get close to something but never quite reach it. Well, that will become clear when I draw it in a minute. For now, I think something that is a quite nice idea is to look at the floor function and see that the floor function is kind of very nicely behaved between integer points. So it might be worth putting some integer points on this axis, and we're told to go up to 3, and trying to understand what exactly is happening between those points. So between 0 and 1, we know that floor x is just 0. So fx in between 0 and 1 is just 0 over x, which is 0. So in fact, for every point between 0 and 1, we can, terrible, but you get what I'm trying to draw. We can just draw the line 0, and that's what the function looks like. Just redraw that a bit nicer. Then, kind of in a very similar vein, we can look at what happens when x is between 1 and 2. Then floor x, that should be a 1, sorry, not a 0. Floor x equals 1. So fx equals 1 over x. Well, actually, we know how to sketch 1 over x. You've probably sketched 1 over x a lot of times in your life at this point. So we know that it starts somewhere here at 1 and ends somewhere here at about a half. Well, exactly a half, but it's probably not exactly a half by the way I've drawn it, and does something like this. And similarly for x, I keep writing 0, for x between 2 and 3, we know that floor x is 2. So fx equals 2 over x. So it has kind of the same shape. It's not immediately obvious where I should draw it, but if we just check it, well, f2 is going to be about 2. So at 2, 2 over 2 is about 1. Did I say 2? I meant 2. Sorry, I'll write it down. f2 is 2 over 2, which is 1. And I'm going to write in quotes f3 is 2 over 3, and we'll come back to exactly why there are quotes there, but something like, noting that 2/3 is bigger than a half, this. Now we need to do the left-hand side of the graph. So it's worth asking what happens when -1 is between x 0, then floor x is -1, and we get that fx equals -1 over x. This is now where the asymptote that someone was talking about earlier comes into play. -1 over x at 0 blows up. And it blows up to positive infinity because for x less than 0, this is going to be positive because you've got a minus sign up front. So we get a graph that kind of looks like this. Now this line will never actually, if we extend this axis and this line upwards, they'll never meet each other, but they'll get very, very, very close. In fact, as close as you'd like. So that's what an asymptote is. And -1 over x is 1 at -1, so we can sort of draw something like this. Then we could continue our graph. Let's just do one more region explicitly and then I'll finish the rest. We have that floor x is -2. I keep writing 0, God. So fx is -2 over x. So at -1, this evaluates to 2. And then it comes back down to 1 here. And then the last region I'll just fill in, but you can check. Looks very similar, but evaluates to 3 over 2. Now, the only other thing to be careful about is what exactly is happening at these integer points. Well, if x is an integer, then we've already discussed that floor x is equal to x. So fx is just equal to x over x equals 1. So we should be getting the value 1 at every single one of these integers, which means if we're using our kind of closed circle, open circle notation, we should have an open circle here and an open circle here, open circle here, open circle here. So we've sketched fx, we've done the first part of the question. Is that clear to everyone? Everyone understand what's going on? Anyone want to make any comments? Is that, guys, what you kind of, what you guys kind of did when you had a go at it? Something similar or different? So far, so good. That's what I drew, very good. Very nice. Okay, seems to be some sort of positive response. If you didn't manage to do that, that's completely fine. You know, anything that kind of, any kind of method that you use to get the graph in some region perhaps is a very, very good step in the right direction. And it's completely normal to not be able to make much progress when you're this early in your kind of school career. Oh, can I move down? There we go. All right, this is just an extra one I put in. And here's a computer doing it for us. You can see it looks pretty similar. I'm now gonna unashamedly use the computer sketch for the rest of the question, but obviously you would usually use your own sketch that you drew. So moving on to the next part of the question. By considering the line y equals 7 over 2 on your graph, or otherwise solve the equation fx equals 7 over 12. I think I said 2, but I meant 12. Okay, so solving an equation fx equals 7 over 12 graphically, are we happy with the idea that if you have a function, any kind of function like this, and you want to solve fx equals 7 over 12, if you draw a horizontal line at 7 equals 12 and look for the crossing point, that's a solution to that equation. That's something that you guys hopefully may have seen before, maybe not. But in any case, it kind of makes sense because at this point, the function is evaluating to 7 over 12. So the question we have is where exactly is 7 over 12 on this graph? Well, helpfully, we can see that 7 over 12 is definitely less than 8 over 12, which when I divide fractions is 2/3, and it's certainly bigger than 6 over 12, which is 1 over 2. I think I divided those right 2 times. Yeah, exactly. So we remember from our graph up there that this value here, this was 2/3, and this value here was a half. So it's between these values. So the line looks something like this. Not very straight, but you get the idea. The important bit is what's happening, that it's below this and above this. So then we know that there's one solution, we can find it. And okay, it's obviously, here we only have the function drawn between -3 and 3. So, you know, maybe there's something out over here, but we can kind of see from the pattern that we had going that actually the function's going to get closer and closer and closer to looking like 1 over here. So this is only going to increase, and this is always going to be above 1. So we can definitely be sure that there's only one solution. And if we solve that solution, well, we're looking for an x between 1 and 2, we can see from our graph. So then we know that fx in this region is 1 over x. So we're looking for 1 over x equals 7 over 12, which we can solve to see that x is 12 over 7. And just as a sanity check, we can see that 12 over 7 is definitely between 1 and 2. So that's correct, and that's the only solution. Oh God, what happened? Okay, it's back. Happy with that? General idea? Again, I'm going quite fast. Yep, cool. And then it's a very similar process for 17 over 24 and 4 over 3. Quickly check that 7 over 24 is less than 18 over 24, which dividing by 6 is 3/4, and it's definitely greater than 16 over 24, which dividing by top and bottom by 4 is 4/6, so that's 2/3. Could have divided by something bigger. Oh well. So now we can imagine that this line going in the 3 to 4 region, extending our graph, this is going to be at 3/4. So our solution is going to look something like that. Badly drawn line, but you get the idea. Extend off to the left. So we're going to have two solutions this time. One here, one here. I'm going to go a bit quicker now because we need to. We lost quite a bit of time at the beginning. So we're going. The first solution we have fx is 1 over x. So we're looking for 1 over x equals 17 over 24, which is. Oh, it doesn't matter if you haven't seen this. Okay, maybe I shouldn't write that. Which is x is 24 over 17. Again, that's between 1 and 2, so that's good. The second solution should be between 2 and 3, so we're going to look for something that's 2 over x equals 17 over 24, which means that x equals 2 times 24 over 17, which is 48 over 17. It can make sense. 17 times 3 is 51, and 17 times 2 is 34, so that's definitely between 2 and 3. And those give us our two solutions. Let me just I've got an answer back here, so let me just double check that I haven't mucked up any of the algebra there. Yep, looks right to me. Okay. Then we've got the final line. We've got to do 4 thirds. 4 thirds is bigger than 1, so it's going to be on the left. Remember that this one was 2. This one is 3 over 2. The next one is actually going to be 4 thirds, and then it's going to come back down towards 1. So we're going to get a line that looks like this. Oh, okay. Well, okay, it's supposed to be less than. I'll just kind of cheat. It should be more like this. But the point is that it's below this one and above, and it goes through this one. We remember that actually at -3, the function is taking the value 1, not 4 thirds. So again, we should look for two solutions here and here. For the first one, we're looking between -2 and -1. So we need -2 over x equals 4 thirds. So x equals -8 over 3, which we can see is between, oh God, -2 over x. Oh yeah, I can't multiply. This is what you get for stepping out steps in your algebra. X equals -2 times 3 over 4, which is -8, oh my God, 6 quarters. And that's definitely between -1 and -2, so that's good. I saved myself with a sanity check there. Saw that my answer was actually in this region, which is good because I suck at algebra, so it's good to check. And then the other solution we should see between -2 and -3, so that's -3 over x equals 4 thirds, so x equals -3 times 3 over 4, which is -9 quarters. That's definitely bigger than 2 and less than -2 and bigger than -3. So that fits our sanity check, and we know that to the left, the graph's going to continue looking more like this. So those are going to be our only solutions. Again, that was a bit fast, but people generally okay with that? Or yeah, people correcting my terrible algebra. Thank you. Cool. All right. Did I just give myself an extra one? Yes. Okay. Next part of the question, find the largest root of the equation fx equals -9 over 10. Well, now this is going to be way off to the right of what we've drawn here, because here we're looking at values that are 2 over 3, and we're looking at a half. So 9 over 10 is going to be way this way. But now we kind of have to stop relying on our graph so much and think about what exactly is happening to the right. So I mean, we can draw the line on the graph. It's definitely going to be bigger than these two. And the question is, what's the last one it's going to be in this? What's the last interval? So the last pair of integers. So let's call them n and n plus 1. So for example, 2, 3, 1, 2, where we're going to have a graph that looks like this. We know that this is going to be 1. We know that this value here, we're in this interval fx, is equal to n over x. So this is going to be n over n plus 1. Well, actually, it's going to take the value 1, but it's going to look like it should take the value n over n minus 1 if we kind of come from the left. So if we imagine drawing the line, for a bunch of them, it's going to cross like this. And then after a certain point, it's going to look below like this. Any ideas as to which interval we should be looking in here? 8 and 9, yeah. There's kind of two that it seems like you should look at, 9 and 10 and 8 and 9. And if we imagine what's going to happen at 8, 9 and 10, well, it's going to be 1, 1, 1. It's going to come down to 8 over 9, and then it's going to come down to 9, badly drawn, 9 over 10 just above it, like this. So when we draw a line, it's going to go through this point, and then from then on, it's going to go above it because we're going to get closer to 1. And the important thing to remember is, drawing it kind of badly here, it should look more like, here's our line, and it's going to come down to exactly this point. Remember that at our integer points, it's taking the value 1. So actually this isn't a solution at 10. So the largest solution is going to happen between 8 and 9. So we should look for something of the form 8 over x equals 9 over 10, which tells us that x equals 8 times 10 over 9, which is 80 over 9. And we can quickly check 9 times 8 is 72 and 9 times 9 is 81, so that's definitely between 8 and 9. And we know that there are going to be no solutions bigger than it, so that's the largest root of the equation. Again, I'm going quite fast. Does that make sense to people? Yes? There's about 4 people or 4 or 5 people who are typing. Okay, okay. Seems to be happy, perfect. Last part of the question, give necessary and sufficient conditions in the form of inequalities for the equation fx equals to c to have exactly n roots. Well, fx equals c is just drawing this horizontal line at c and then seeing how many times it crosses the graph. So if we imagine starting our line, let's not start it here, let's start it below the axis when it's negative, we can see that it's not going to cross the graph at all. So for c less than 0, there are 0 roots. And now the question becomes, as we push this line upwards slowly, we hit the graph more and more and more and more, and we need to count the number of roots that we're getting. So the first time we hit the graph is at c equals 0. Well, at c equals 0, the whole of this, this bit here is equal to 0. So there are infinitely many roots. You know, every number between 0 and 1 works. So that's the first time we hit the graph. And then we imagine moving our line into the next region, which is going to be here. We don't hit the graph again until we get to a half. So for c between 0 and a half, we get 0 roots again. So this is just pushing our line slowly upwards. Then when we hit a half again, okay, yeah, Mail's just put a thing in the chat. If you're not don't want to say something to everyone, just direct message it to one of them, and you should be able to click the to everyone. There's an arrow, and just message it to one of them, and then they can pass it on to me anonymously. When we hit a half, this is a half, and then this is 2/3, etc. There's only one possibility for where it could intersect, which is here. But actually remember that at the integer points, f is taking 1, as we've said quite a few times. So actually, it's less than or equal here. When we hit half, we don't get any roots. Now, when we go just over a half, suddenly we do get a root. We get a root, you know, something here maybe. And when we go a little bit over a half, so we don't hit 2/3 yet, we get 1 root. So for between 2/3, we get 1 root. And actually we can see that again for integer points 1 reasons, at exactly 2/3 we only get 1 root because the function is taking 1. And then if we imagine the next section of the graph, which goes between 3/4, if we have c greater than 2/3 and less than 3/4, we're going to have 2 roots. And this kind of follows the same pattern. If we have c between n over n plus 1, c is less than or equal n plus 1 over n plus 2, we're going to have n roots. And you can kind of see this through just doing it a couple of times manually and checking, or you could go through with all the details. But I mean, this is perfectly enough working to be able to jump straight to, oh, this is obviously what's going to happen as we continue. Now, n over n plus 1 and n plus 1 over n plus 2 get very, 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 very close to 1 as n gets very large. You know, like, 99 over 100 is very, very close to 1. But we're never actually going to quite hit 1. So the next case to consider is what happens when c equals 1. Well, then, as we've said quite a few times at this point, all of the integer points are solutions. So again, there's infinitely many roots. And now, when we push just above 1, we've got a lot of weird stuff happening to the left. So when we do the next side of the graph, which I believe I've given my say sort of perfect, it might make sense to come from above instead, because for c very big, it's obvious that we only have one root from this asymptote at x equals 0. So for c greater than, and we can see that this value is 2, we're going to have one root. And actually, because of the integer points, -1 is taking the value down here, it's actually c greater than or equal to 2. Then the next jump happens at 3/2. So for, the next point of interest happens when we go just below 2 and above 3/2. So for 3/2 c2, we have one root. 2 roots, sorry. We have one in this region and one in this region. And again, for integer value point reasons, when we hit 3/2, we still only have 2 roots, because actually the function is taking the value here. And then we can continue in a similar fashion. If we did one more, it's going to be, this one is going to be 4/3. So we had 4/3 less than c, we're going to have 3 roots. And then very similarly before, you can sort of generalize this to a pattern straight away. You know, we have n+1/n is less than or equal to c is less than n/n-1. Then we have n roots. And for here, we need n greater than or equal to 2, because if n is 1, bad things are happening because we're dividing by 0. And then we're done, because this is going to get closer and closer and closer and closer to 1, this n+1/n on the left hand from above now. And we've already got closer and closer from 1 to below. So we can summarize all of the conditions that we had. We had n+1. Okay, let's write them all down. So c less than 0, no roots. C equal to 0, infinite roots. And then hang on, I'll just steal them from where I had them before. n/n+1 less than c less than or equal to n+1/n+2 has n roots. And this time we're looking at n greater than or equal to 1. Then when we hit 1, we have infinitely many roots. Then when we have n+1/n less than or equal to c less than n/n-1. So notice that the inequality less than or equal sign has swapped sides here. We have n roots. And then when c is greater than or equal to 2, we have one root. And this time we have n greater than or equal to 2, because we don't want to divide by 0. And then we're done. Written down here, they seem quite intimidating because there's a lot of them. But when we were doing them back up here, they kind of followed quite systematically. And that's the entire question. Did that make sense to people? Happy? Any other questions? You can ask questions that aren't just about maths, by the way. If you've got any questions about student living or studying experiences. All good? Yep. Good. Generally happy. Anyone do the question differently, or? Good. Okay, people mainly seem to be happy, so I guess we'll move on. Okay, we'll move on to an unseen question now. So I'd hope to have a bit more time than this, but I guess we can try and maybe do the first 2 parts, and then the last part you can have a go at yourself. So this question is from 2006. I'll give you guys a couple of minutes to read it. Hopefully you can all see it. I'll zoom in a little bit so that it's clearer maybe. So I'll give you guys 1 minute to read it. Any initial impressions or positive vibes or negative vibes? Chuck them in the chat. I'll start talking again at 44. Use to discriminate, yeah. Good ideas. Okay, So hopefully you guys have had enough time to at least read the first bit. So this is kind of the opposite kind of question to what we had before. Before it was something new, now it's quadratics and cubics, which are hopefully something you guys have seen probably quite a lot at this stage. So more familiar territory, but that means probably the algebra or the thinking is going to be a bit harder than in the previous case. So first of all, this is the kind of question that talks about sufficient and necessary conditions. This is something I definitely did not understand when I did STEP. So I just thought I'd quickly give an example of necessary and sufficient conditions. Hello, can I have my pen back, please? No? Okay. So if we talk about animals for a second, an animal that has stripes may not be a tiger. A tiger has stripes. These are hopefully things that you would agree with. For example, zebras for the first one. And this is an example of something which is necessary but not sufficient. If you have stripes, you are not necessary, you don't have to be a tiger. So having stripes is not sufficient for being a tiger. But if you are a tiger, you do have stripes. So having stripes is necessary for being a tiger. So that's an example of something that is necessary but not sufficient. I write NESS for necessary, mainly because I can't spell it, and sufficient as SUFF. Something that's the other way around, so something that's sufficient but not necessary. If it's raining, the weather is bad. If the weather is bad, sorry for my terrible handwriting. If the weather is bad, it might be snowing. So if it raining is sufficient for the weather to be bad, but it's not necessary because it could be snowing instead. So that's something that's sufficient but not necessary. And hopefully this question will give you some more mathematical examples, but that's something that I definitely did not understand when I did STEP, and it's something that comes up a fair amount, so it's probably worth wrapping your head around. For the first part, considering the graph y equals x squared plus b, x plus c, show that c less than 0 is sufficient for this equation to have distinct real roots. So it says by considering the graph, so we should probably draw some axes. And it says that c is less than 0. Well, luckily, c has quite a nice interpretation. It's the y-intercept. So this is c, and it's less than 0. And we can pretty easily see that no matter what our quadratic looks like, it could look like this. It could look like this kind of thing, or it could look like this kind of thing. That's 3 examples. I probably should have drawn them in different colors, but oh well. In every single case, we have 2 roots. In the first case, we have them here and here. In the second case, we had them here and here. And in the third case, we had them here, here, and here. So if c is less than 0, it is definitely true that our graph has 2 real roots. So you probably should write something down if you're doing this as a question, but I won't bother. That's pretty quick. So we move on to the next part of the question. Is it necessary for the equation to have distinct real roots? Any thoughts? Nope. C equals 0 has a root. That's true. No. Okay, yeah. There's 2 ways you could go about this. First of all, you could try and draw a picture with a c greater than 0 that has distinct real roots. That's fairly quick to do. You could draw something like this. Or you could try and write down an equation that has distinct real roots and c greater than 0. Depends on the sign of x squared. So this is something that I initially thought when I was doing the question as well, but actually we're only interested in graphs that are of the form x squared with x greater than 0, with a 1 in front of the x squared. So it's definitely going to be kind of like a U shape rather than an upside down U, because we're forced with this sign choice. You're completely correct. If x squared was less than 0, if it had a negative coefficient in front of x squared, we could have something that looks a bit more like this. But in this case, we've got an upside down U. Sorry, we've got a U rather than an upside down U. So here we've got a case where c is greater than 0, and we've got 2 distinct real roots. we could equally, kind of informed by this, if we imagine that they're at 2 and 3, write down the quadratic x minus 2, x minus 3, which has roots at that's 2 and 3, and this is x squared minus 5x plus 6. So this is definitely got distinct real roots. So in general, c less than 0 is sufficient for 2 real roots. I guess I should write distinct instead of 2, but but it's not necessary. People okay with that? Any other questions? Okay. No questions, seemingly fine. All right. Moving on. Mail, you're muted. I don't know if you're trying to talk, but you have to unmute yourself first if you are. For the next part, I guess we'll start the next part. Show that c less than 0 is sufficient. No, that's the same question. But determine necessary and sufficient conditions for this square to have distinct positive real roots. Well, that's having distinct real roots, and they better be positive. Well, if we draw a graph, so this is the kind of graphical approach, if we have distinct real roots, we've got something like this. So our quadratic better, that is truly one of the worst quadratics I've drawn in my life. Oh, awful. Try again. Slightly better, not very good. Oh well, you get the idea. The quadratic will look something like this. So we're going to end up with c greater than 0. There's also something with this minimum, but it's not immediately clear what this b means on the graph. So here it probably makes a bit more sense to do some more algebra first. So I'm going to do this quite fast because we don't have much time. We can write this as x plus b over 2 squared plus c minus b squared over 4. That's completing the square. And we want this thing to have 2 roots. Well, that means it better be able to equal 0, which means that x plus b over 2 squared equals b squared over 4 minus c. Well, for that to have any solutions, in fact, distinct solutions, this side better be greater than 0. That's necessary, and it's also sufficient for there to be different solutions. So necessary that we have b squared over 4 over c, b squared over 4 minus c greater than 0, which we can just rewrite as b squared is greater than 4c. That's necessary for 2 distinct roots, let alone them being positive. We want them to be positive, so let's look at the roots. Well, we can quickly write them down as this thing. So this is the quadratic formula that you're probably familiar with, but we've just got it from completing the square instead, which is actually how the general formula comes from anyway. But and we want these to be positive. Well, since you want both of them to be positive, it's easier to check just the smaller one, because if the smaller one's positive, then the bigger one's definitely positive, and they're both positive. So you want this to be greater than 0. Let's save that and move on to the next page. Well, we want a minus sign here. Well, the thing under the square root is definitely, this thing is definitely positive because it's a square root, and the square root of any number, if it exists, is positive. So subtracting it is definitely negative. So if this thing's also negative, then we're going to end up with a negative minus a negative, which is going to be a negative. So we definitely need this term here with the minus sign to be positive. So we need minus 2 over b to be less than 0, which means that we need b, greater than 0, which means that we need b less than 0. Does that make sense to people? That's a bit quick with the inequalities there, but hopefully that makes sense. Yep, cool. So negative numbers are scary, so let's let k equal minus b. Then we're left with k over 2 minus k squared over 4 minus c, because k squared and b minus b squared and b squared are the same thing. And we want this to be greater than 0. Well, we can quickly rearrange that. This side is definitely positive because k is greater than 0, because minus b is greater than 0. This side's positive, so it's a square root. So we can kind of square that without really worrying about whether this is true in two directions. So you get that c is greater than 0, which is actually the thing that we saw kind of straight away from the graph. So to summarize, we've found three conditions. C greater than 0, we needed b less than 0, and we actually need, I'm going to write this the other way around because it fits nicer. We also found that we needed c for c less than b squared, and for c being greater than 0 is obviously the same as c being greater than 0, so you don't have to worry about that, which we got for was the condition up here. And in fact, you can check that these are sufficient. If 4c is less than b squared, there are two roots from this kind of stuff up here. These are those two roots, and this number is positive, and this number, b squared minus a number that is greater than 0, is less than that number. So when we square root it, we end up with something that is less than b over 2. I'll just write that out a bit more clearly over here. If we have b less than 0 and c greater than 0, then b squared over 4 minus c is definitely less than b squared over 4. Then we square root both sides, and we notice we've got this 4c minus b squared, so this side definitely is all good. It's greater than 0. So when we remember that b is less than 0, so when we square root it, we get this. This is the positive answer. So minus b over 2 minus b squared over 4 minus c is greater than 0. So we do get two positive roots. So these three conditions here are necessary and sufficient. That one was a bit more algebra-y. It's harder to do with the graph. You can get all of these exact inequalities from finding the coordinates of this point here and insisting that it happens at a positive x and a negative y, but we don't really have time to go through that. We definitely don't have time to do the last part of the question either, so we'll stop there. Any questions about that last bit? That bit was that was fast because again, we didn't have much time. I've got a wow, thank you. Okay, any other questions at all? So to do with anything we've said today, or applying or studying here, or anything like that? You don't have to have a question, but if anyone does, it makes sense to ask them now. If not, I think we're supposed to stop at 4, right? Otherwise, I think Dr. Spivak will take us back to the main room in about 3 minutes. Anything that you'd like to add, Mael or Andrea?
Not especially. Yes, yes, Dr. Spivak will bring us back to the main room when necessary. If any of you students have any question to ask, like, it's a good opportunity to do so. There is me, Wolfram, and Andrea who's there as well. If you have a question about life in Cambridge or anything.
It's worth pointing. I'm a third year, Mael's a second year, and Andrea's first year, I think. So I've got a range of. You're welcome. How do you rate the course out of 10 so far, and why? I would rate it 10 out of 10. I have loved it. There is so much variety and stuff you can do, and so much flexibility and stuff you can do here versus other universities. So I've been able to do so much interesting stuff that I wouldn't have an opportunity to do elsewhere. For example, this year, quantum computing and information computing, which is something that's basically offered at no courses anywhere except for Cambridge. So that's cool. Mael, you got any?
Yes, there is an incredible amount of diversity in what we can choose, and there is really like also a gap between the course before the second term of the second year and after the second term of the second year. Because after the second term of the second year, we just have so many courses, we usually don't choose them all. We choose like whatever we really like. and we get we can get as specialized as we want or as diverse as we want. And as you said, it's an incredible like opportunity to do what you like. I even know, like in fourth year, if you're interested in something and there's no course about it, you can ask teachers whether you can be examined on it, and they'll just give you books to read and like, which is crazy.
It's amazing how much diversity there is. Probably get on to the other questions. Someone asked about workings after the session. Yeah, this will be going up on YouTube afterwards, and all of the notes that I wrote down will be going up as well. What am I aiming to do after university? I want to do a master's. Then I get scared about that kind of question, so I don't know.
And well, I'd like to do a master's and then a PhD, and then I'd like to go and work for some government or like the UN, because they're looking for statisticians to make like data analysis to help making decisions.
That sounds very cool. Do any specific year 2/3 options require specific further math modules? No. So what you'll find is that in first year, you basically spend all of your time, you go a lot further than A-level, but you start from a point which you will definitely be able to do. And then from then on, once first year just builds you up all of the skills that you will need for second year and third year. Well, not obviously you need some of the stuff from second year for third year, but after first year, you'll definitely be able to do all of the second and third year options if you make sure you pick prerequisites. So don't worry about your further maths modules. Think about that more for STEP in terms of whether you like mechanics or stats.
Yeah, especially like in first year, there are people from all around the world who arrive, so they haven't all taken the same syllabus. So everything is built from the very beginning, although it's multiple, as both would said.
Yeah. Would you say the step from GCSE to A-level is harder than the jump from A-level to uni? They're very different. Going from GCSE to A-level, you do a lot of subjects in depth, but you have a bit more variety. Going from A-level to uni, obviously uni is a lot harder and different than A-level, but you have a lot of time just to dedicate to uni, so they're difficult in different ways. I don't think either of them is necessarily more obviously harder than the other one. I don't know what you guys would say to that.
I think, yeah, the step from doing everything like within school to doing it on your own, like I found the hardest, but that's just more getting used to like making my own schedule rather than the actual maths. So
that's true. There is an ability to just sit in your room all day and watch Netflix, which you have to force yourself to not do, which obviously isn't there in school. I think we'll get kicked out any minute, but we might as well keep answering questions if anyone else has any. I guess I'll say a little something about STEP preparation. Don't be put off by STEP. Oh, okay, someone actually has another question. Howley, first year, everything you are forced to do, so it's compulsory, half of it's applied, half of it's pure. In second year, you can probably specialize if you want to, but I think most people don't specialize that early. They probably go like 70%, 30%. And then by third year, you're probably specialized. Again, you don't know, you don't have to be. You can stay in with a foot in both.
I think second term of second year is when you can really specialize. Like first term of second year, you could, but it's kind of risky, but because there aren't that many courses. And then from the second term, there's like a lot, and you can do only pure if you want.
Or only applied, if you're applied maths is definitely better. When did you know that this was the course for you? I looked at the courses online, and this one just had so many different ones, and they're also taught by so quantum information and computing, which is something I was talking about earlier, that is taught has a theorem in the course called something called the Deutsch-Jozsa algorithm, and Professor Jozsa is a professor at Cambridge who teaches the master's course equivalent. So it's pretty cool. You get taught by people who are like literally founders of the fields, which is not bad. Career options most popular with math graduates. I think there's something on the website about that, but from memory, it's like 50% go on to do masters or further study, and then a lot go and work in like IT, and then some go and work in finance. I think those are the big ones.
Yeah, I just say, so I don't know exactly, but I think there's a cliche about everyone going to the city after, and like, that's not the case.
No, definitely not. I have no interest going into the city. I mean, it is great if you want to go into the city. I mean, there's our math course actually has like modules on modeling financial markets and stuff, which I'm sure is useful if you want to go into that. But it's definitely not something that you have to do. Anything else? Have you looked at the Oxford Open Day or looked at Oxford stuff? Anyone? Not yet. Good answer. The courses look quite similar. Okay. Yeah, I mean, they're both pretty good, other than the fact that Cambridge is way better. I think there's also very unbiased, absolutely. There's also a difference in the way that the entrance exams work and when exactly your entrance exam comes and the percentage of people that get interviewed and stuff. But I'm sure you'll find out about that. Anyway, it's all right. No worries. It's this or revision, so it's better than revision. How my interview experience is. Oh man. 50% of my interviews, well, okay, I had 2 interviews. So one of my interviews was great. And it was by Professor Gog, who's, if you're applying to Queen's, you'll know about her, who was lovely. And with someone called Dr. Saxon, also lovely. And I came out of it feeling really positive. And then the other one, I felt like crying afterwards, but apparently, I still got in. So, advice for the interview. I think 2 things. Don't be afraid to be guided. So if they're hinting at something, they're not trying to trip you up or anything. Use their hint and try and be guided by them. And also practice just talking about what you're doing. So I forced my parents to listen to me talking at them as I did an A-level question a couple of times. And it really helped me get used to saying things as I was doing them. That was quite helpful. I applied to Queen's because someone told me it was a good idea. That's not a good reason to apply to a college. Do more research than that, but Queen's is great. I think location, accommodation cost, how many years you get on site, what kind of formality and formal halls and stuff there are things to look at. But I mean, you will end up loving your college if you do get in, I'm sure. There isn't a general interview question for maths. There's lots of examples online. But yeah, there's no one question that they'll definitely ask you. Are we supposed to?
Well, Andrea, okay. What's your college?
I go to Trinity.
Oh man.
Yeah, I don't know. I just really enjoyed the vibe because I like the old buildings. I like the size of it, so that was good.
Oh, okay. We got 55 seconds. Last minute questions. Actually, what college are you at, Mel?
I'm in Hamilton. Yeah, ooh, just one thing. Do look out for college. It's true you'll end up like loving your college anyway. Also, I don't think there really is a difference in teaching quality between colleges, but there is a difference in like lifestyle, like how much you'll go out if you're in the city center or not. So I think this is definitely the one thing that will help you make a decision about college. I think the breakout room is going to close now.
Yeah. Well, good luck, everyone. I hope to see you all in 2 years, 3 years, 3 years, 2 years. I don't know, some number of years at Cambridge. Yeah. We should leave. Bye.
Bye.
Great. I think that's the end of all the breakout rooms. Thanks, everybody. I hope that was useful. Bye-bye.